Cars are a major part of our lives that make it easier to move around. But if you needed your car to do more, such as handle driving in the snow or carry large objects, well, you'd probably modify it by adding winter tyres or hitching a trailer to it. In a similar way, Python is a powerful language that allows developers to build amazing things, but it can gain even more functionality with the use of modules. In this video, you'll learn about modules in Python and why they are used. You'll also explore the different types of modules and be able to explain where they can be found. Now, you may wonder what a Python module is. Imagine that modules work like instructions to make a pie. Instead of trying to figure out what the steps are to create your pie, you follow the instructions. Modules work in the same way. They are building blocks for adding functionality to your code, so you don't need to continually redo everything. A Python module contains statements and definitions. So a file like sample.py can be a module named sample and can be imported. Modules in Python can contain both executable statements and functions. But before you explore how they are used, it's important to understand their value, purpose, and advantages. Modules come from modular programming. This means that the functionality of code is broken down into parts or blocks of code. These parts or blocks have great advantages, which are scope, reusability, and simplicity. Let's delve deeper into these. Everything in Python is an object, so the names that you use for functions, variables, and so on become important. Scoping means that modules create a separate namespace, so two different modules can have functions with the same name. And importing a module makes it a part of the global space in the code being executed. Reusability is the most important advantage of modularity. So when you write a piece of code, modules help you avoid the need to write all the functionalities that you may need. Duplication of code duplicates your efforts, uses more computer memory, and it's less efficient. Let's say, for example, you want to import a math package. You automatically get access to a lot of functionalities, such as factorial, the greatest common divisor, used as GCD, and so on, that are reused without defining them. One other feature that using modules brings is simplicity. When modules have a little dependency on each other, it helps achieve simplicity. So each module is built with a simple purpose in mind. Modules are defined by their usage. So you can also use a regular expression or RE module for managing regular expressions. Simplicity also helps in avoiding interdependency among these modules. So if you're working on data visualization, import of a single module like matplotlib is sufficient for visualizing your data. There are different types of modules that exist in Python. The main difference between these modules is the way the modules are accessed. Let's cover built-in modules. Some modules are already built into the standard Python library. When you use a statement like import math in your Python code, for example, the interpreter first tries to find built-in modules. So, how do you import and execute modules in Python? The first important thing to know is that modules are imported only once during execution. If, for example, you import a module that contains print statements, print, open bracket, close bracket, you can verify it only executes the first time you import the module, even if the module is imported multiple times. Since modules are built to help you, standalone modules hold all the functions, but will most likely not contain functions that execute without calling. It's only when the user executes the different functions inside that module that they will find the utility of those functions in the code. The module is normally defined at the beginning of the code, but you can define it at any point in the code. Since code execution in Python is serial, you must import the module first before you execute any function inside of it. Modules can also be executed from within the function. This means that the code inside that module can only be used once the function is executed. In this video, you covered modules in Python. You learned about the different types of modules and how they can be used to save you time and make your work more efficient. In Python, you can access different types of modules, such as built-in modules and user-defined modules from different locations. Think of the built-in modules as a house that you want to build using pre-built and packaged floors, walls, and a roof that you can just assemble. This means you don't have to try and find hammers, bricks, plaster, and tiles to build walls and floors, saving you time and making your work more efficient. Accessing built-in and user-defined modules in Python works in the same way and helps to save time and build efficiency while you're coding. Remember that any Python file can be a module. The modules are searched by the interpreter in the following sequence. First, the current directory path. Second, the built-in module directory. Third, the Python path, an environment variable with a list of directories. And finally, it investigates the installation-dependent default directory. Let's explore this in greater detail. In this video, I'll demonstrate how to access different types of modules, such as the built-in modules and user-defined modules from different locations. Let's write some code and learn how to access some built-in modules. I begin by creating a new file called myCalendar in Visual Code. I then use the sys.path function and return the values that I get from it in a variable called locations. I finally print the values using the print function. I now try running this code. Unfortunately, this does not work as Python has no idea what sys is. To resolve this, I'm going to try and import the built-in sys function. I'm going to run the code again. The print function returns all the possible locations that the interpreter is going to look for when searching for modules, including the current working directory. But this doesn't look very clean. I know that I have a list of values, so I'll run a for loop that loops through every location in turn. This returns a much cleaner result by printing each location on its own line in the terminal. Now, it's always good practice to import all the required modules right at the beginning, but I can do this in a different way. I'll import a module here in the middle of the code. I'll import another built-in module called calendar. I'll now use a couple of functions that the calendar has. I'll now use a function called leap days, which has two inputs, year 1 and year 2, and it will be returning another integer value. So what I'm going to do is write the leap days function, write 2 input years, and return the value in a variable called leap days. I'm going to print the value of the variable. I get a return value of 13, which means there are 13 leap days in between 2000 and 2050. Now I'll use another function. This function is called isLeap. It takes one of the years as an input and returns a Boolean value. It tells you if a given year is a leap year. So let's try 2036 and return the value in another variable called isItLeap. This time I get the value of true because 2036 is a leap year. If you decide to explore a little bit, you can hover over calendar. If you use a MacBook, press the Command key, or if using Windows, press the Control key, which will take you to the calendar file by clicking on it. Note how the calendar module itself has imported a few other modules, and other than that, it contains all the functionalities. I now find the location of calendar inside the Python 3.9 package, which is one of the locations listed in the terminal by the print locations loop I ran earlier. You just learned how to access built-in modules and user-defined modules from different locations. I encourage you to start using modules in your code to make your work more efficient.
In this video, you will learn how to use import statements for accessing modules from different directories. You will also learn how to create packages from the Python package index using pip. Every Python file, which means any file with a .py extension containing a script, is effectively a module. The check imports file I am currently creating is therefore a module for some of the files. The code that you are working with is generally called the main module. In this case, check imports is the main module present in the current working directory, also called the scope of the project. You can import any Python file that is present in the current scope. For example, I can import the sample.py file by typing import, followed by the file name without the extension. I then click on Run in the top menu. The system returns a message in the terminal pane that the import was successful. If I try to import a file with a .txt extension, the import will not be successful. For example, if I type import followed by sample text and click on Run, the system will return an error message in the terminal pane as it is not a Python file. Python has a library of standard modules called built-in modules. These modules are directly built into the Python interpreter and don't have to be installed separately. I can import a module like JSON by typing import JSON. Once I execute the command, I can start using its functions directly. The list of built-in modules can be found in the Python standard library. You can think of packages as the structuring of Python modules as a collection. Special files called init.py files are required for Python to treat directories containing the file as packages. Python has a rich collection of community-built packages that I could find on the Python package index, or PyPI. Pip, or pip3, is the default package installer for Python and helps with the installation of packages from PyPI. Since I have already installed NumPy, I can import it directly in Python. I do this by typing import NumPy, clearing my terminal, and clicking Run. If I try to import a package that is not installed, I will get an error message. For instance, if I type import Seaborn and click Run, the message module not found error is returned. If the package Seaborn were installed, I could run the command again in Python without any error messages. To do this, I would run pip install Seaborn in the terminal to download the package from the PyPI index. I can also import files I have created in one of the folders within the current working directory. I have a folder called Workplace, containing a file called trial.py. The file consists of a list with the variable names and 2 entries inside it. I'm going to import this file and access its contents. I start by importing the sys module. Next, I use a path function in sys by typing sys.path.insert. Now, I must enter the path name to my workplace package in the first index location. To do this, right-click on the workplace directory and select Copy Path. I enter this path name as the first index location. When passing the path as an argument, I must use single quotes and type the letter R in front of the path string. The sys.path list now has a new directory where it will look for modules. Now I must import my trial file here by typing import trial and pressing enter. A squiggly line appears below the word trial. This is because the IDE does not know about the path I've added inside sys.path. However, I can still proceed as the interpreter will know about this path. To print the output, I type print followed by trial.names and click the run button to execute. The values of Adrian and Maria from the names list variable are printed. In this video, you learned how modules can be imported from anywhere within your system. Inserting the path name can, however, be very specific and often tricky and confusing. Don't worry about this too much for now. It is more important to focus on importing files from your current directory. It is nice to know that importing modules from other directories is an option if you need it. It is good practice, though, to move the required files into the directory that you are working in. Let's explore how to use modules with the import statement. I have already created a file called imports.py. I will now import the built-in math module by typing import math. Just to make sure that this code works, I'll use a print statement. I do this by typing print, importing the math module. After this, I'll run the code. The print statement has executed. Most of the modules that you will come across, especially the built-in modules, will not have any print statements, and they will simply be loaded by the interpreter. Now that I've imported the math module, I want to use a function inside of it. Let's choose the square root function, sqrt. To do this, I type the words math.sqrt. When I type the word math, followed by the dot, a list of functions appears in a drop-down menu, and you can select sqrt from this list. I pass 9 as the argument to the math.sqrt function, assign this to a variable called root, and then I print it. The number 3, the square root of 9, has been printed to the terminal, which is the correct answer. Instead of importing the entire math module as we did above, there is a better way to handle this, by directly importing the square root function inside the scope of the project. This will prevent overloading the interpreter by importing the entire math module. To do this, I type from math import sqrt. When I run this, it displays an error. Now, I remove the word math from the variable declaration and I run the code again. This time, it works. Next, let's discuss something called an alias, which is an excellent way of importing different modules. Here, I assign an alias called m to the math module. I do this by typing import math as m. Then I type cosine equals m dot. I then select cos, C-O-S, from the list of functions, after which I add the number 0 in parentheses. On the next line, I'll print cosine, and then I run the code. The result is the cosine value of 0, which is 1. This is possible because I used the alias called m. If I tried writing math.cos, it wouldn't work because the math module is now recognized as m instead. Let me remove this code from the screen and clear the terminal before we continue. An alias can also be used for a function that's imported. For example, I can type from math import factorial as f to alias the factorial function. Now I assign f of 10 typed as f opening parenthesis, the number 10, and a closing parenthesis to a variable called factorial 10. I'll print the variable and see if it works. When we run the code, we see that it works just fine. Using an alias in this way reduces the effort of typing factorial every time. After I remove the alias, I can import as many functions as I'd like from a given module. I'm going to import log and sqrt. I create a variable using the log function to find the value of log base 10 of 50. I do this by typing x equals log 10 opening parenthesis 50 and closing parenthesis. And again, I print the variable on the next line. And when I click run, I'll see whether or not it worked. Once again, it worked just fine. Now, what if I want to import all the functions inside a given module? I can remove the functions I added earlier and replace them with a star. This basically translates to import all from the math module. When I run the code again, let's see if it works. And it does. However, this practice of using a star is not the best approach in certain cases. For example, this is a small file, and I know that the log10 function is present inside the math module. But when you work with a large codebase, it can be difficult to track where the log10 function came from. Additionally, when you're importing other modules, it may get confusing. Importing packages is very similar to importing modules in Python. Just like you can have imported functions, you could also import variables and classes from a given module. Now I replace the star with a variable called SomeVariable, which may be present inside the given module. Let me try to run the code again. Since the math module doesn't have such a variable, it throws an error when I print it. The interpreter is not able to import SomeVariable from math. In this video, you explored different methods that can be used to import modules in Python using keywords like import from, star, and as. This enables you to use the modular structure of Python in object-oriented programming in general.
Now you should be fairly familiar with how modules work. Let's look at another related concept in Python, namespaces and scopes. The official Python documentation defines namespace as mapping from names to objects, and scope is the textual region of a Python program where the namespace is directly accessible. At this point, the dictionary, with its key value pairs, serves as the ideal data structure for the mapping of names and objects. You have also learned how every Python file can be a module. You can view the same module as a place where Python creates a module object. A module object contains the names of different attributes defined inside it. In this way, modules are a type of namespace. Namespaces and scopes can become very confusing very quickly, and so it is important to get as much practice of scopes as possible to ensure a standard of quality. There are 4 main types of scopes that can be defined in Python: local, enclosed, global, and built-in. The practice of trying to determine in which scope a certain variable belongs is known as scope resolution. Scope resolution follows what is known commonly as the LEGB rule. Let's explore these. Local. This is where the first search for a variable is in the local scope. Enclosed. This is defined inside an enclosing or nested functions. Global. is defined at the uppermost level or simply outside functions, and built-in, which is the keywords present in the built-in module. In simpler terms, a variable declared inside a function is local, and the ones outside the scope of any function generally are global. Here is an example. The output for the code on screen shows the same variable name Greek in different scopes. There are three possible declarations of the variable. At the global level, inside the function b, or inside the nested function c, which is called from within b. The id function is used here in the print statements, which returns the identity of the objects. You can make some observations from the output. The ID for the global variable alpha remains same as defined after the code is completely executed. The ID for the local variable beta inside the function b remains unchanged before and after the execution of nested function c. The ID for gamma is assigned only within the scope of the nested function, and the ID for all three variables is different even if they all have the same variable name. Variables in Python are implicitly declared when you define them. That means, unlike other programming languages, there is no special declaration made in Python for the variable which specifies its data type. What it also implies is that a given variable is local, not global, when it is declared, unless stated otherwise. This contrasts with most other programming languages where variables are global by default. So, when a variable is declared in a global space, it is also local to that space. This can be understood with a simple example. If you look at the content of both of these dictionaries, you can see how the value for the key country is different in both the cases. You have also used two special built-in functions called locals and globals that list the contents of the dictionary inside both of these scopes. Here you can see the output. In this example, you can see the global variable declared remains unchanged. While global variables are acceptable, they are discouraged for a number of reasons. When you are working with production code, the project structure can get complex, and working with global variables can be hard to diagnose, which lead to what is called the spaghetti code. Other paradigms such as access modifiers, concurrency, and memory allocation are better handled with local variables. While you are just beginning our journey using Python, it is always a good idea to integrate good practices in your code. There are two keywords that can be used to change the scope of the variables: global and non-local. The global keyword helps us access the global variables from within the function. Non-local is a special type of scope defined in Python that is used within the nested functions only in the condition that it has been defined earlier in the enclosed functions. Now you can write a piece of code that will better help you understand the idea of scope for an attribute. You have already created a file called animalfarm.py. You will be defining a function called d, inside which you will be creating another nested function, e. Let's write the rest of the code. You can start by defining a couple of variables, both of which will be called animal. The first one inside the d function and the second one inside the e function. Note how you had to first declare the variable inside the e function as non-local. You will now add a few more print statements for clarification for when you see the output. Finally, you have called the e function here, and you can add one more variable animal outside the d function. This will be a global variable. You can add a call for the d function and a print statement for the global variable. You can save this file and run the code. First, the global animal variable gets assigned camel. Then, call this function, and once inside it, assign elephant to the local animal. Then, declare the inner function e, and proceed by printing before calling functions animal, where the value of animal will be the local value, which is elephant. Once you are inside the inner function e, you use the non-local keyword to declare that you are going to use the animal variable, and you change the value to giraffe, and here you can see that the print statement will give inside nested function the value is giraffe, which stays consistent even after you get out of the inner function. So when you print after nested function, the value still remains giraffe. Once the function is fully executed, come out to see that the value of global animal will be camel, which you had assigned at the beginning. So you can see the changes that you have made inside are not going to affect the value of the global variable. Let's look at one last thing. If you comment the local variable out, this will throw an error. You can see there is no binding present for non-local animal present inside the D function, which was required here.
In this video, I'll cover the reload function that's used with import statements. The reload function reloads an imported module in Python. The only precondition is that the argument passed to it must be a module that has already been successfully imported within the program. Previously, you learned how the import statement is only loaded once by the Python interpreter, but the reload function lets you import and reload it multiple times. I'll demonstrate that. First, I create a new file, sample.py. And I add a simple print statement named hello world. Remember that any file in Python can be used as a module. I'm going to use this file inside another new file, and the new file is named using reloads.py. Now I import the sample.py module. I can add the import statement multiple times, but the interpreter only loads it once. If it had been reloaded, we would have seen hello world several times. However, I can change this with the help of the reload function. Let me remove this code and add the import lib module where the reload function sits. Then, I pass the module name as an argument to this function. Note that the sample module has been imported more than once, and I could do it as many times as I want. Now, to better demonstrate how the reload function can be used, I'm creating another file called filechanges.py. This file is going to list the content of a particular directory. In the following code, I will be updating the contents of the directory and be able to monitor the changes using a file that I will import. Since the interpreter loads the file only once, the reload function will allow us to reload that import and effectively update the changes every time without stopping the execution of running code. I begin by importing the built-in OS module, and I use a function called os.listdir inside it. Next, I pass the current path as an argument by right-clicking the Files tab at the top and selecting Copy Path. I paste this as an argument to the listdir function and add an R before the path. Because I'm looking for a directory and not a file, I remove filechanges.py from here. I'll save the output from the listdir function into a variable called contents. On the next line, I'll add a print function for the contents variable. Before running our program, I'll clear the terminal to make things clearer. The return value should list the files that are present in the given directory. You'll notice that it indeed lists all the files present in this directory once printed. I now go back to the reloads.py file and I clear the file. Then, I once again import the import lib module. After this, I import file changes and create a function called changes. As good practice, I add a try block and use the reload function to pass file changes as an argument. Let me go back to the filechanges.py file and create a function that will print the contents variable. This is now complete, but I'll add another print statement for clarity. I save this file, and then I go back to using reloads.py. I call this function that I just created inside the file changes module, and because I want to make a try block work, I add the except and just pass for now. After this, I execute the code using a for loop. Because I want to do it more than once, I use the range function and call the function that I just wrote. To take some control of the program, I'll add an input statement here. Now the program will execute 5 times, and every time it will load the file changes module and list the contents of the directory. To make it more interesting, I'm creating a few text files inside the directory. Now I've returned to using the reloads.py file to run this code. Note that the content of the current directory is listed here, but I'll now remove the text file called text3.txt. When I execute the code again by hitting enter, you'll notice that the particular text file has been removed. Now, without changing anything else, I'll execute the rest of the code. If I also change the content of filechanges.py, for example, changing the print statement before the file names, I could see the code reflected after I press enter again. As I demonstrated, the reload function can be used for making dynamic changes within your code with the help of import statements.
Packages are bundled collections of modules in Python serving a specific purpose. In Python, there are currently tens of thousands of packages to choose from, and in this video, you'll learn about some of the most popular. You can think of this collection of packages like a traditional real-world library. Each package is a book or magazine, and this library gets bigger every day. In programming, a package is a directory or folder, and in the same way, a module is a file or document. You import packages in the same way as a module using the import statement. And like with the import statement, it's important to remember that unless defined correctly, the import serves no purpose. For example, suppose you want to import a package named foo. The import statement on its own will not serve any purpose. It needs to be in a format like from foo import a, where foo is the package and a is the module containing the functions you want. Exploring the package's directory structure or referring to code blocks online can save time. To work with packages in Python, it's important to know that pip is the default package manager, and Python Package Index, or PyPI, is the package index where you can find and publish packages. Python has an extensive collection of packages. As a developer starting out, it can be overwhelming, but it's important to understand what Python is most widely used for today. The major application areas for Python are data science, AI and machine learning, web frameworks, application development, automation, and hardware interfacing. With this in mind, packages can be grouped into categories. For example, built-in packages, data science, machine learning and AI, web and GUI development. Let's explore each of these briefly now, starting with built-in packages. These are packages that don't need to be installed separately and can be used as soon as you've installed Python. Almost every project uses one or more of these built-in packages, so it's worth getting to know them well. The most popular ones are OS, sys, CSV, JSON, importlib, re, math, and itatools. In the world of data science, the most popular Python packages are NumPy, SciPy, NLTK, and pandas. These are all used for data exploration and manipulation. Other packages like OpenCV and matplotlib are used for image processing and data visualization. Within the world of machine learning, or ML, and artificial intelligence, or AI, the most popular packages are TensorFlow, PyTorch, and Keras. PyTorch and Keras are currently the most popular for deep learning and neural network implementation. There are other packages such as SciPy, scikit-learn, and Theano. Choosing which package to use will depend on the scale and scope of the project and how familiar you become with the package in question. Okay, let's move on to web development. Python today is primarily used for ML, AI, and web development. The most popular packages are Flask, which is a lightweight micro framework, and Django, which is a full-stack framework. Other popular web development packages include CherryPy, Pyramid, Beautiful Soup, and Selenium. There are also other packages for robotics, game development, and other specialized domains. For any domain you want to work in, you'll find several Python packages relevant to it. While no one package may be a perfect fit for your current project, the open source community of Python developers is working relentlessly to fill the gaps. As a beginner Python coder, most functions you need will be met by one package. To continue expanding your knowledge of Python packages, you should think of a project you'd like to create and experiment with the packages I've mentioned in this video. In this video, you learned about packages in Python. You covered built-in packages and some of the most popular packages in use today. Python is one of the best languages to use for various data science projects and applications. In this video, you'll learn about some of the commonly used Python libraries in data analysis and data science. The last decade has seen exponential growth in all data science areas. The demand for data analysis and scientists is continually increasing, as it's a requirement for developers to incorporate scientific and data analysis into their code. Python has emerged as one of the most popular languages with data scientists. One of the main reasons for its popularity is the large number of different open source packages. These have been developed by thousands of contributors collaborating to provide free, usable resources. Many packages are top-rated because they are efficient and provide outstanding functionality. In no particular order of preference, these packages include NumPy, SciPy, Matplotlib, and scikit-learn. As an example, scikit-learn is used for predictive learning and is built on top of other popular packages. It consists of various supervised and unsupervised machine learning algorithms for classification, regression, and SVMs. Modeling data is the primary focus of this library, and it provides popular models such as clustering, feature extraction and selection, validation, and dimensionality reduction. Pandas is an acronym for Python Data Analysis, and this is a data analysis and manipulation tool. It's used primarily for working with datasets and provides functions for cleaning, analyzing, and manipulating data. Using it, I can compare different columns and find the arithmetic mean, max, and min values. The primary data structures used in Pandas are series and data frames. While series are single-dimensional and can be compared to a column in a table, data frames are multi-dimensional and can potentially store tables efficiently. They are agnostic to the data types being stored. Pandas' most common applications are reading CSV files and JSON objects and using them within Python code for faster retrieval. Pandas are known to bring speed and flexibility to data analysis. Pandas library is normally imported by the code import pandas as PD. NumPy stands for Numerical Python and is a powerful library forming the base for libraries such as scikit-learn, SciPy, Plotly, and Matplotlib. Python scientists use the abilities of NumPy especially when working in scientific domains such as signal, image processing, statistical computing, and quantum computing. NumPy carries out the calculations needed for algebraic areas such as Fourier transforms and matrices. The backbone data structure in NumPy is called ND-array or n-dimensional array, which substitutes the conventional use of lists in Python and is a much faster solution than lists. The dimensions in NumPy are called axes, and the number of such axes is called a rank. Conventionally, NumPy is imported with import NumPy as NP. Matplotlib is the visualization library used in Python. It can be used to create static, interactive, and animated visualizations. Many third-party tools such as ggplot and Seaborn extend the functions of Matplotlib. These functions are located inside the pyplot subpackage. Matplotlib is imported with import matplotlib.pyplot as PLT. An example such as libraries 2.0 uses the Matplotlib and NumPy libraries to, for instance, display a graphical representation of students in a class or the distribution of their scores. To recap what you've learned in this video, you should now know about the most commonly used Python data analysis and data science packages. Artificial intelligence, or AI, is broadly about making machines think like humans. Data science primarily focuses on the management and exploration of data, which may include media such as text, audio, images, and video. Machine learning, or ML, is a subsection of AI and deals with algorithms for training and generating insights from data. Many fields utilize machine learning. Some of the most widely used areas are natural language processing, deep learning, sentiment analysis, recommender engines, computer vision, and speech recognition. With the amount of text, image, and video data available today, data science and AI in particular are in greater demand than ever. Python is one of the most popular languages used in these domains. The reasons are syntactical efficiency and readability, flexibility with different languages, frameworks, and operating systems, a welcoming and large community of developers, ability to build ML models without having to understand the intricacies, user-friendly debug and testing tools, and modular structure. These all promote the development of many primarily open source libraries and frameworks. It's important not to get confused with the terms, packages, library, and frameworks. A package is a collection of modules, and both library and framework are often used interchangeably with packages. Libraries can also be a collection of packages with specific purpose, whereas the term framework is usually used where certain flow and architecture is involved. It's important to remember that all of these pieces of Python code are used with the help of import statements. Some of the most popular ML libraries in use today are in the areas of deep learning and neural networks, computer vision and image recognition, natural language processing, data visualization, and web scraping. It's important to understand that these are broad categorizations. Most of the libraries associated with them are not restricted to a particular field. Every project is unique and should be treated as such. The right selection of the library can save precious time when coding. In this video, you learned about machine learning libraries. Many fields use machine learning, and those fields, like deep learning and neural networks, rely on open source machine learning libraries that make developers work easier. These libraries are collections of packages, and the selection of the right library can save you time when coding. So in the future, think carefully about which library you should pick for a project to make sure that it suits your needs. Web frameworks are software applications designed to provide us with a standard way to build, deploy, and support web applications that we can use on the web. They help developers to focus on application logic and routines by automating redundant tasks, which helps cut development time. They also provide easy structuring and default models that are reliable, stable, and easily maintainable, saving time and effort. Web frameworks are primarily written in high-level code, which removes the overhead required for understanding concepts such as sockets, threading, and protocols. As a result, time is better spent working on application logic instead of routines. Python is a popular framework in web development thanks to several features such as good documentation, abundant libraries and packages, ease of implementation, code reusability, a secure framework, and easy integrations. The different frameworks in Python are efficient and make it easy to handle tasks such as form processing, routing requests, connection with databases, and user authentication. They also provide debugging and testing tools to handle profiling, test coverage, and test automation, etc. There are mainly three types of web frameworks in Python. These are full stack, micro frameworks, and asynchronous. Let's explore each briefly now. Full stack frameworks are considered a one-stop solution and usually include all the required functionalities. This can include form generations and validators, template layouts, HTTP request handling, WSGI interfaces for connection with web servers, and database connection handling. Some of the most popular Python frameworks are Django, Web2Py, and Pyramid. Micro frameworks are a lighter version of full stacks that do not offer as many patterns and functionalities. They are usually used in smaller web projects and building APIs. Flask, Bottle, Dash, and CherryPy are some of the popular micro frameworks. As the name suggests, asynchronous framework types are used to handle a large set of concurrent connections. They are mainly built using async.io networking libraries. Growler, AIO HTTP, and Sanic are some of the names you'll encounter. Choosing a framework can depend on many factors. This can include things like available documentation, scalability, flexibility, and integration. While this categorization is pretty broad, it's important to remember that each framework in Python has its own unique set of features and functionalities. This can make certain frameworks more suitable than others for a specific project. Two of the most widely used are Flask and Django. Let's explore each briefly now. Django is a high-level framework that encourages clean design and rapid development. It's a full-stack framework that's rich in features and libraries. It's secure and has templating systems and third-party support. It primarily gained popularity due to its rapid deployment speed. You can quickly build scalable apps without extensive knowledge of low-level programming. Flask is a micro framework and better used for smaller projects. It's easy to learn, simple to use, and has a large library of add-ons. In this lesson, you learned about web frameworks and the different types. You also learned about the different web frameworks in Python, such as Flask and Django. Testing is an essential component in quality assurance that ensures our software, applications, and websites work as expected. For example, suppose you've built your own website and it has a few hundred visitors every day. One day, an article you've published goes viral. Suddenly, 1 million people are visiting your site and the website crashes. Another scenario is online forms. We've all faced situations where we fill out a form and a prompt appears telling us that we have made a mistake. For example, accidentally entering letters in space provided for credit card numbers or missing special characters in passwords. This type of data validation is even more critical, especially in the domains of banking and finance. In this video, you'll learn about testing and its importance in the software development lifecycle. But what exactly is testing? Well, software testing is a process of evaluating and verifying the various software applications and products in terms of performance, correctness, and completeness. It helps identify bugs, gaps in the product, defects, and missing requirements with set expectations. In the early days of computers, software developers relied heavily on debugging, a process for removing and detecting potential errors. After the 1980s, as software grew in size, several different testing types and products also grew in parallel, depending on the requirements. Testing was primarily done in the later stages of the software lifecycle. Now it's evolved to be integrated at the early stages as well. The efficiency of any testing type is dependent on how well written it is. The ideal testing scenario is to have the least tests written to find the largest number of defects. While software testing is important in any scenario, the real test of the product comes when it's launched to market. There, it's judged by stakeholders and users. We live in the internet age. Products with bugs, especially in the early stages, make consumers lose interest very quickly as many alternatives are available. This is where testing plays an important role, and here are a few reasons why it can help. Testing helps detect poor designs, change inefficient flow or functionality, address scalability concerns, and find security vulnerabilities. Testing helps provide A/B testing to find the best suitable options, address compatibility with platforms and devices, provide assurance to stakeholders, and a better experience for end users. There are a few good practices that must be followed in testing to achieve optimal results. Test code allowing reusability of tests. Tests must be traceable to the requirements set. Tests written must be purpose-driven, efficient, and allow for repeatability. These testing techniques can then follow a procedural approach according to the type of testing used. The testing lifecycle in general can be broadly described as planning, preparation, execution, and reporting. The steps involved in achieving this can include writing scripts and test cases, compiling test results, correcting defects based on them, and generating reports from our test results. Okay, so you've already learned about test cases. They are a general set of actions containing steps, data, pre- and post conditions written for a specific purpose. This purpose can improve functionality, flow, and finding defects. A well-written test case eventually provides good coverage, reusability, better user experience, reduces costs, and increases overall satisfaction. As the tech industry is ever growing, several testing categories, types, tools, and products have evolved, which are tailored to best meet the requirements of the software in question. For example, a web page will have different testing needs than an Android-based game. Even among web pages, a social media page will differ from one, say, from financial management. Testing can be categorized by several different factors. For example, depending on the amount we know about the internal implementation, we can call it black box or white box testing. There are also many testing types used in practice. These include compatibility, ad hoc, usability, and regression testing. Don't worry too much about these terms for the moment. You'll learn more about them later. For now, I just want you to know that with testing, there is no one-size-fits-all solution. When testing products, it's also important to understand when to stop, as no application will ever be 100% perfect. Otherwise, a developer may feel the product is well tested, but realize it's full of bugs and flaws as soon as it's released to the end users. A few metrics can be established for this purpose, given that there are well-written test cases in place. These include a certain number of test cycles, passing percentage of test cases, time deadlines, and time intervals between subsequent test failures. Testing in software development can be seen as the anchor of a ship or insurance for your vehicle. You can hope that everything operates smoothly, but often it does not. And while you can aim for perfection, there is always potential for human error. Quality assurance today has become an important component in the software development life cycles. Much of the credit goes to development of testing tools and techniques. The question is, what type of testing should you use? In this video, you'll learn about the types of testing, including the 4 main levels or categories of testing, which is unit, integration, system, and acceptance testing. There are different ways in which you can categorize the different test types. There are white box and black box tests. White box testing is where the tester has knowledge of the code, design, and functionalities. Black box tests function with no such information, and the tester has no idea about the internal implementation. There are also other ways to categorize different tests as functional, non-functional, and maintenance tests. Let's explore these. Functional tests are based on the business requirements stated. They determine if the features and functionalities are in line with the expectations. Non-functional tests are more complex to define and involve metrics such as overall performance and quality of the product. Maintenance tests occur when the system and its operational environment is corrected, changed, or extended. But there are also manual and automated testing methods that are dependent on the scale of the software. The most broadly accepted categorization is in terms of the levels of testing as you move ahead in the software lifecycle. Let's delve deeper into these levels of testing. The 4 main levels of testing are unit or component testing, integration testing, system testing, and acceptance testing. The 4 types of testing levels build on each other and have a sequential flow. Let's explore these now. In unit or component testing, the program tests specific individual components by isolating them. The components are low level, which means that they are closer to the actual written code. They often involve use of automation for continuous integration given their small sizes. So you usually write these tests while writing the code. For example, if the code is in Python, unit tests can be written with packages such as PyTest. Integration testing combines the unit tests and tests the flow of data from one component to another. The keyword here is an interface. This means that you test if the data is correctly fetched from a database within the Python code and if you have sent it to the web page. There are different approaches to it, such as top-down, bottom-up, and sandwich approaches. Your approach depends on what code level interfaces you attempt first. It builds on the unit testing and a tester deals with it. Next is system testing, which tests all the software. You test it against the set requirements and expectations to ensure completeness. This includes measurements of the location of deployed components, such as reliability, performance, security, and load balancing. It also measures operability in the working environment, such as the platform and the operating system. This is the most important stage handled by a team of testers. It's also the most critical stage, as the shipping of software to the stakeholders and end user happens after this phase. The final type of testing is acceptance testing. When the product arrives at this stage, it's generally considered to be ready for deployment. It's expected to be bug-free and meet the set standards. The stakeholders and a select few end users are involved in acceptance testing. It normally involves alpha, beta, and regression testing. One way of approaching this is to give pre-written scenarios to the users. You use the results for improvements and try to find bugs that were missed earlier. All the different testing levels are designed to optimize software at different stages. The key to testing is testing early and testing frequently. While each of the testing phases is important, early detection saves time, effort, and money. As the code gets increasingly complex, mistakes become harder to fix. It doesn't necessarily mean that unit testing will happen only at the beginning and acceptance at a later stage. There are many testing cycles where these levels are approached iteratively. A typical example is the Agile model. Here you release different versions of the product iteratively and you perform acceptance testing every few weeks. In this video, you learned about some of the types of testing such as unit testing, integration testing, system testing, and acceptance testing. It's important to remember that the purpose of these testing methods is to build a systematic approach for testing and identify faults and improvements as early as possible. This results in improved overall performance and experience. Well done. With advancements in technology, an increasing drive is towards code automation. In this video, you'll learn about test automation packages and the importance of automated testing. In the past, machines have substituted human effort in making goods, which helps us save both time and effort. In programming, the tests chosen for automation are the ones that have high repeatability and volume, predictable environment and data, and determinant outcomes. There are a number of testing types that can be automated. These include unit, regression, and integration. An ideal test code must form a bridge between the programming calls and the test cases. Python does a fine job in achieving this in addition to its clean, concise way of coding. There are some well-written frameworks in Python, and some are more well accepted than others. The ideal steps involved in test automation are usually preparing the test environment, running the test scripts, and analyzing the results. Okay, let's now examine some important Python testing frameworks that have grown in popularity over the years. First, let's explore the built-in testing package, PyUnit or Unitest. The Unitest framework supports test automation, independent testing modules, and aggregation of tests into collections. The first is PyTest, a native Python library that is simple, easy to use, and reasonably scalable. PyTest will be demonstrated later in this course. It can handle several functional test types such as unit, integration, and end-to-end. There is support for parameterized testing, which enables us to execute unit tests multiple times with different parameters passed. It can run parallel tests and generate HTML, XML, or plain text reports. You can also integrate it with other frameworks like PyUnit and Nose2 and web frameworks like Flask and Django. While primarily used with testing APIs, it's also well used with UI, database connections, and other web applications. Easy creation and quick bug fixes are why PyTest is the most popular testing framework for automation. Next is Robot, which is popular primarily for its keyword-driven development capabilities. These keywords are used in test cases and can be predefined or user-defined. Robot is very versatile and used for acceptance testing, robotic process automation or RPA, and test-driven development. It can be used for many domains including Android, APIs, and mainframes. Selenium is another open source testing framework that has gained popularity over time and is primarily driven towards web applications. It has support for the majority of web browsers and OS. There are browser-specific web drivers that enable testing functionalities like login, button clicks, and filling of forms. It allows the tester to select the speed and execution of tests and has an option to run specific tests or test suites. Apart from the popular frameworks PyTest, Robot, and Selenium, there are many more. It's important to know that a number of these testing frameworks are often used with other tools such as plugins, widgets, extensions, test runners, and drivers. These tools help integrate the software pieces being tested and add functionality. Sometimes more than one framework is employed over the code being tested. In this video, you learned about test automation packages. Let's recap quickly. Automation testing is an important reason why the software industry is able to move ahead swiftly and more smoothly. Manual testing provides focused attention and the ability to handle nuances and complex problems with more sophistication. This kind of testing can't be replaced by automated tests yet. It's still some time before test scenarios can be fully automated, but the developments of all these frameworks are in line with that endeavor.
In this video, I will demonstrate how to use PyTest to create simple tests for unit testing. PyTest is one of the most popular modules for unit testing in Python. This is because it allows you to do simple tests with minimal effort. And it also has simple, clean code with good documentation. First, I create a file called addition.py. Next, I add a function and pass two variables, a and b, inside it. I'm just going to do a simple calculation that will return the sum of these two variables. Similarly, I create another function called sub, which will perform the subtraction between the two variables. Second, I create another file called testaddition.py, in which I'm going to write my test cases. Now, I import the file that consists of the functions that need to be tested. Next, I'll also import the PyTest module. After that, I define a couple of test cases with the addition and subtraction functions. Each test case should be named test underscore, then the name of the function to be tested. In our case, we'll have test underscore add and test underscore sub. I'll use the assert keyword inside these functions because tests primarily rely on this keyword. It checks for conditions in your code and expects a Boolean value of true or false. When the return value is true, the test passes. When it is false, the test fails. Let's add assert statements to our tests. In our first test, we'll assert that the addition of 4 and 5 is 9. And in the second test, we'll assert that the subtraction of 4 and 5 is -1. Next, I make a split screen so that I could see both files. Now, I run PyTest, and I specify the file over which I'm going to do the testing. To do this, open a new terminal and enter python -m pytest and the name of the test file, testaddition.py. I ran the code and both tests passed. This means that both the assert statements have been confirmed to be true. 4 plus 5 is 9, and 4 minus 5 is -1. These two dots after testaddition.py in the terminal also indicate that both tests passed. Now, I will intentionally make one of these tests fail. I do this by changing the -1 answer to -2. I make sure that I have saved the file, clear my terminal, and I'll run the test again. Note that the first test passed, but the second one didn't. Also note that where there were previously 2 dots, there is now only 1 dot and an F to indicate that the second test failed. The E's at the start of the lines show where the test failed, and it supplies the possible reason as to why it failed. I can also write these tests without the assert statement and just add pass. This passes the test regardless of any errors. When I run the code again, it indicates that both tests passed. You should note that I used an equality operator here, but I could have used less than, greater than, or keywords such as is, in, or not in. All that matters is that the assert statement gets a Boolean value. I can also add multiple assert statements in a single function. So, if I write assert true, that should return the result. And when I run the code again, it passes both tests. But if I make it false, it will show that one test has failed. This indicates that all the assert statements within a given function should return a true value for the test to pass. Note that using the test underscore prefix for both the file name as well as the function name is good practice. Now I'll restore my code and save the file. If I want to run my test over a specific function, I just add a double colon at the end of the file name, and then I write the function name. I'll clear my terminal first, then run my code. Note that only the function I specified has run. Congratulations! You now know about simple functions. In this video, you learned that you could use PyTest to implement unit testing and how to create and use simple tests for unit testing.
Testing has been a relatively recent entry in the software development lifecycle, but its importance has been growing as time passes. Software development is time sensitive, and in the process, developers often find testing gets squeezed into the time remaining after the code is written. This doesn't leave enough time to test and can lead to the software containing bugs that need to be dealt with over time. Test-driven development, or TDD, is an alternative programming practice in which the tests are written first and the code is written so that the tests will pass. This differs from the convention of first writing the code and testing the application progressively. TDD follows an iterative approach beginning with writing the test cases. The initial work requires feature and test planning by the team. With slight variations, let's explore the standard steps. Step 1. You write a test for a feature that fails. In step 2, you write code in accordance with the tests. Step 3 requires that you run the test expecting them to fail. In step 4, you evaluate the error and refactor the code as needed. And finally, in step 5, you rerun the process. This process is also called the red-green refactor cycle. Red implies the failed tests, and green shows the passing tests after refactoring. The whole point of following this cycle is to fail the tests and rewrite until you don't have to. A feature is complete when everything is green, and you no longer need to rerun. You can use a package library such as PyTest when automation becomes a priority. PyTest only requires writing functions, while Unitest requires classes. This means that PyTest has the advantage of being easier because it requires less effort. Okay, now let's explore some of the advantages you gain from TDD. Writing tests first and refactoring code based on it ensures the tests cover the code. You can now write tests with a specific feature and outcome in mind. The need for such forecasting provides clarity from the beginning. The forecasting also plays a role in integrating different components where you add new features and interfaces in accordance with the components that are already there. Working in cycles over the code gives the developer confidence to easily refactor in terms of additional changes. Overall, smaller code with early bug fixes, code extensibility, and eventual ease of debugging are the primary reasons TDD is growing in acceptance. Finally, let's briefly explore some of the differences between TDD and traditional testing. The main difference is that with TDD, the requirements and standards are highlighted from the beginning, making it purposeful. Modern-day development often employs a combination of both these forms of testing, depending on the different parts and stages of the software development cycle. There are several subtypes and variations of test-driven development. These include behavior-driven, acceptance test-driven, scaling, and developer test-driven development. These are all options that can be used in the software development process. Congratulations! In this video, you learned about the process of test-driven development. In this video, you'll learn about how to apply the test-driven development methodology. In conventional testing, you follow the process of writing code and then writing test cases to ensure the integrity of that code. In test-driven development, or TDD, the approach is the other way around, and test cases are where you must begin your thinking. The steps involved are as follows. Write test cases with some functionality in mind. Write code in accordance with the test cases, ensuring that they pass. And refactor code in case the tests fail. Let me demonstrate an example to design a test case that checks student enrollment with data stored in a database. The test needs to check the integrity of the names entered. First, I'll demonstrate how to design the test case and then write some code. Let's say I'm checking student enrollment for a class exam against a list of names that I already have. To keep things straightforward, I'm going to use a Python list with the names instead of a database. I want to make sure that the names I enter are on the list. And I also want to ensure data integrity, which means that I must be sure that the names are entered in the correct format. I've created two files. The first is test_findString, which is my testing file. And the second, findString, is my main file. I already have the PyTest package installed. And because this is test-driven development, I'll write my test function first. I begin by importing a curses module that will help me check the ASCII characters that are present. Then I import the PyTest module, as well as the findString module, which is my main file. I define a function named test_isPresent, and I add an assert statement to check if the isPresent function works, because I'm going to use it to validate my data entry. Contrary to the conventional approach of writing code, I first write test_findString.py, and then I add the test function named test_isPresent. In accordance with the tests, I create another file named filestring.py in which I'll write the isPresent function. I define the function named isPresent and I pass an argument called person in it. Then I make a list of names written as values. After that, I create a simple if-else condition to check if the passed argument is present inside the list. So the function called isPresent will check if the name passed is present in the list. Let me test my code. Note that the test has passed because the name Al is in the list, but this doesn't ensure the integrity of entries I may add. For example, I might not want numeric characters in the names. To address this issue, I write another function named test_noDigit. I'm going to update some of the code in my main program findstring.py in accordance with the newly added test. To do this, I create a function called noDigit that matches my test. And again, I create a simple if-else condition. I run the code and you'll note that one of the tests have passed and the other one has failed. So the name Al passed because it's on the list of names, but the value of N7 didn't pass because it contains a numeric character. I could also add more test cases and modify my code so that it's suitable for the test cases, and I can repeat the cycle until I have no more failed tests. Congratulations! You've now explored the test-driven development methodology.